Hello everyone, welcome to the series Wireless Census Networks by MaxcoTec. This is the fifth part of the series in which we are going to look at data collection and one of the most basic technique used in data collection called floating logarithm. This video covers definition of data collection and why do we need it, what is the motivation behind it. Then we will look at floating logarithm definition and the basic logarithm, proceeding with two advanced logarithms, asynchronous and synchronous, and what is the difference between them. Then we will look at some properties of floating logarithm, including non-determinism, message complexity, and time complexity by giving you the real-world example use cases. In the end, we are finally going to conclude floating logarithm that is going to give you a good picture of where this logarithm stands as compared to two other very famous logarithms known as gossip and tree, which we are going to cover in the next videos. So let's get started.
Data collection, a procedure technique to gather data wirelessly from unattended nodes installed on the remote fields. The idea and the motivation behind this is it's inconvenient and expensive to send resources into the field to collect data from every single node. That's why data collection techniques allows us to send a trigger at a single node wirelessly, which propagates the data collection request to all of the other nodes in a network. One of the way is the distributed data aggregation, where the data is processed on its way to the sink. In this way, all of the nodes work equally to save energy, because eventually processing cost is much lower than the transmission cost. In a dense network, data is correlated, so aggregated functions like min, max, average, sum over the data in a whole network are often more important than the data of the individual nodes. So let's say for two temperature nodes who have found themselves so far in the network, one of them collects the temperature from another one and sends the aggregated value of both the temperatures to the third one, and so on. Finally, the last node gets the overall aggregated value of the temperature of the entire network. Other way is quite similar to the first one. Instead, nodes see the network as a rational data, where users can control and monitor network's health and status by using SQL queries. There are three types of data collection approaches: gossip, tree-based, and floating. I've constructed it in a triangle to define the properties of each. So let us look at the floating first. In the data floating technique, the word floating is taken literally. Data is simply floated into the network, which is, as a result, utilizes every path on a network, including the shortest. It is indeed quite simple to implement. The algorithm looks something like this. So we start off with some specific node, let's say Ni. Ni sends the message M to all of its neighbor nodes. When NQ receives the same message from one of the neighbor of Ni, which can be like NP, if NQ has never seen this message before, it is going to forward it to its neighbors, else NQ is going to discard that message. So in asynchronous, each node runs its independent exponential clock of rate 1. Nodes perform actions upon its clock tick. There is a 0.001% of probability of two clocks ticking at the same time. There is a non-deterministic message delivery time. I will be explaining this in the next slide, so bear with me. In synchronous floating execution, we are given specified slotted action times. Node performs actions in rounds. A round is a time between each slot where the message is sent, delivered, and processed. And time is measured as the number of rounds until termination. So to study about the non-determinism of the floating logarithm, let's take this example as three nodes, where node 1 sends a message to all of the other nodes in a network. So let's suppose message M was delivered to node 3 before it got delivered to node 2. So node 3 is going to follow the logarithm and it is going to forward this message to all other nodes in a network, excluding the node from where the message originated from. So now the node N2 is expecting the same message from two sources, N1 and N3. And let's say the message from N1 to N2 is still delayed and we received message from N3 to N2 before. Then in this case, we are in a situation where this message M is propagated back to its originating node from node N2. So due to this not deterministic behavior of the logarithm, this execution will not be going to be acceptable as part of the logarithm. So this will be discarded. So every last execution is not acceptable, especially in this case as we have described above. So this is the worst case scenario in this floating logarithm. And every execution depends on the order in which they are delivered. So the message M from node 1 could arrive at node 2 before M from node 3 does, which is exactly as I described in the situation above. So studying about the message complexity, or in other words, I would say how many times a message M travels in a network until the execution stops. So we know that each node does not send a message M more than once on each edge. So if node N1 has sent message M to node 2 on this edge, then it's not going to send the same message M on the same edge again. Since there are two nodes attached on a single edge, so message M can be sent at most twice on every edge, which is the worst case scenario as we discussed earlier. So to calculate the total number of messages traveling in the network can be described as total number of edges multiplied by 2, which gives us 6. Now we want to exclude all those edges from where the message originated from. In this case, this edge and this edge. So 6 minus total number of nodes minus 1, that gives us 4. So we can conclude that by increasing total number of nodes, total number of messages increase linearly twice the size of the network. So the message complexity is O(n to the power square). Time complexity, how much time it is going to take for this logarithm to deliver message M to all of the nodes in a network. In synchronous mode, number of rounds needed to spread message M to all of the nodes. The graph diameter is the maximum distance between two nodes in a network. By the time t, message M reaches nodes at the distance of the diameter or less from its originating node. So we can say that the time complexity of this logarithm is exactly the same as the diameter. If the diameter increases, the message complexity increases proportionally. In asynchronous execution, we assume that the time between sending and receiving any message is at most 1. So the time complexity can be said as maximum time until termination among all the timed acceptable execution. So to conclude the floating logarithm, one of the big advantage of this is that it is fast. It starts from a specific node and spreads the message across the network. It is robust. It can cope with errors with respect to any number of nodes in a network. Operation will still be running successfully even if some links fail. And of course, it is simple to implement. Some of the disadvantages of this logarithm is that, as we studied earlier, it is inefficient. So in case where the message M was only destined for one single node, the logarithm passes this message M through all of the nodes in a network. So it is a waste of bandwidth. And the other disadvantage is that due to the duplicate of messages traveling at most 2 times in a single edge, it increases the bandwidth load, which is actually caused by this non-determinism property of this logarithm.
That is all for this video. If you liked it, please do give a thumbs up, and if you have any questions or if you need to appreciate, please do leave a comment and subscribe if you are new to this channel. This is going to keep us motivated to bring such useful stuff to you guys in the future. Next video will be about data collection tree logarithm. So stay tuned. I will see you in the next one. Till then, take care. Bye.